Everything is made of atoms. But what are atoms made of? Scientists used to believe that atoms were solid particles, like tiny snooker balls. They thought atoms couldn't be split apart. This idea was changed in 1897 by J.J. Thomson. He was investigating the properties of cathode rays using this piece of equipment, an empty glass tube. Here's a modern version of Thomson's apparatus, an evacuated tube containing an anode and a cathode. Heat the cathode and it produces a beam of cathode rays. The beam cuts across a fluorescent screen. Scientists knew that a magnetic field could deflect the path of a cathode ray beam. Turn the magnet round and the beam is deflected in the other direction. Thomson measured the size of this deflection. He worked out that cathode rays were made of tiny particles, hundreds of times smaller than an atom. Thomson was also the first to deflect these beams with an electric field. The screen sits between two horizontal charged plates. An electric field between the plates deflects the path of the beam upwards. The positive plate attracts these cathode rays. The negative plate repels. Reverse the connections so that the polarity swaps over and the beam is deflected in the opposite direction. Again, attracted to the positive and repelled by the negative. From this, Thomson concluded that cathode rays must be made of negatively charged lightweight particles. He'd discovered what we now call electrons and went on to say that electrons were part of all atoms. In 1911, Ernest Rutherford made the next major breakthrough in atomic structure. He was examining the results of an experiment based on this type of setup. A radioactive source emits a narrow beam of radioactive particles. This is directed at a target of thin gold foil. Detectors register the presence of radioactivity at different positions. These displays will show the count rate in each detector. The experiment must be carried out in the dark in a vacuum. Start the detectors at the same time, and the fixed detector behind the gold foil shows a high count rate. Most of the radioactive particles pass straight through the metal film. There's a much lower count rate on the other detector. This shows that a few radioactive particles have bounced back from the gold. But how could this have happened? Rutherford suggested that atoms contained a tiny, dense core called the nucleus, surrounded by lots of empty space. Imagine each snooker ball is the nucleus of one gold atom. And these marbles are the radioactive particles. Aim the marbles at the snooker balls. Most roll straight past to be detected behind our model gold atoms. It's this that made Rutherford think that there must be a lot of space within each gold atom. Our model also shows why some radioactive particles were deflected from the gold foil, having hit the dense central nucleus of a gold atom. Following Thomson and Rutherford, scientists have now discovered lots of particles inside the atom. You need to know about three: the proton, the neutron, and the electron. A proton has a positive charge. A neutron has no charge. An electron has a negative charge. The nucleus of most atoms is made up of protons and neutrons. The only exception is the hydrogen nucleus. It contains just one proton. Each nucleus is tiny compared to the rest of the atom, which is almost all empty space. The only things there are electrons orbiting the nucleus at very high speed.